Okay, so we're talking about a ball that is thrown upwards from 3 meters above the ground, and we know its initial speed. We know there's lots of air resistance involved, and we're talking about the ball returning to its initial height, and we specifically know how much energy is lost to air resistance, and we want to know the speed when it returns to its initial height. So let's draw out a quick sketch of this. We've got, let's say, ground level. We've got the ball that starts off 3 meters above the ground. And let's label those, let's say y equals 0 and y equals 3. And then what happens to that ball? Or what are we actually trying to figure out here? Because I think it's often a good idea on questions like this, just skim through it and figure out what's it actually asking. So what is our goal here? What are we trying to figure out?
The final velocity?
Yeah, we want to know the final velocity, final speed, specifically where? Final velocity at what location?
Initial height?
Right. We want to figure out, because we know that it starts off going on its way up at an initial speed of 8 meters per second. And we know that it's going to go up, reach some maximum height, and then fall back down, passing through its initial height 3 meters on the way. So let's say it reaches some final height. We don't know what that final height is, but we can at least label that y max. And then it falls back down. And on its way down, it's going to be passing through that same initial height again. It's just going to be on its way down instead. And we want to know what that v final will be. First of all, just intuitively, would you expect that v final to be the same as v initial, or faster or slower? Probably slower. And why is that? Why wouldn't we expect it to just return to the same speed if it's returning to the same height? Yeah, we've got this this friction, this air resistance force, which is causing a removal of energy. So on the way up, it's losing energy, losing total energy, and also on the way down, it's also losing total energy. So that means its final total energy is less than its initial total energy. So to figure out what that final speed is, let's take a look at this in terms of the changes in energy. What types of energy are changing here? Or actually, before we even look at types of energy, what would we call initial and final here? If we just start listing out values, we've got an initial speed, right? We've got a final speed, which we don't know. So if we're calling this initial and this final, what do we know about the initial height and final height? Yeah, initial height is 3 meters and final height? Also 3 meters. If we treat 3 meters on the way up as initial and 3 meters on the way down as final, then we know the initial height and the final height, and they're both 3 meters. What does that tell you about the potential energy of gravity? From 3 meters to 3 meters, is that an increase? Yeah, overall it stays the same. So even though we have, even though the object is moving, it's going up and then going back down, we've got an increase in potential energy and then a matching decrease in potential energy. the total change in potential energy is going to be 0. And that's really, I think, the main reason to choose those as our initial and final locations. We could choose anywhere as initial and anywhere as final. But if we specifically choose this initial and this final, initial is 3 meters on the way up, final is 3 meters on the way down. That's very convenient because it means we know the initial and final heights are the same. That means overall there's no change in potential energy of gravity. In fact, the only thing that's really changing from initial to final is what? What type of energy is changing? Yeah, we got velocity changing, which corresponds to what kind of energy? Yeah, kinetic energy is changing. Well, it's really more that we can choose anywhere we want as initial and anywhere we want as final. But ideally, you want to choose an initial state and a final state such that one of those is something you know everything about, and the other one is something you know everything except one unknown. So if we choose 3 meters on the way up as our initial, we know the initial height and we know the initial velocity. If we choose same location on the way down as final, then we know the height and we don't know the velocity. So that's only one unknown. You want to set things up so that your initial and final conditions together ideally have only one unknown in them. Or maybe two unknowns if you also have another fact about the situation, so you can set up two equations, two unknowns. You want to set up, you want to have as many facts, as many equations as you have unknown variables. Choosing these initial and final situations mean we have one equation with one unknown variable. And to turn that into an equation, you can start by drawing out an energy interaction diagram, or you could skip this step if you're confident enough to just jump straight to the equation, but you can always go through the energy interaction diagram as a step along the way. We know what type of energy is changing here. From initial to final.
Wait, what was the question again? Sorry.
What type of energy is changing from initial to final?
Kinetic energy?
Yeah, the only thing changing is kinetic energy because we are changing the speed. We're going up pretty fast, and then we're going to be going down, presumably slower, at some unknown final speed. So we should assume the kinetic energy could be changing because the velocity, or I should say absolute value of velocity, because we don't care about direction, is changing. And since we're specifically choosing two locations that are at the same height, same initial height and same initial and final heights, that means potential energy doesn't change at all. There's certainly changes in between. It's going up and then going back down. But the whole point of conservation of energy in this sort of approach, the energy interaction diagram, is that we don't care about what happens in between. We're only looking at the differences between initial value and final value. So there's a change in kinetic energy. We can even fill in indicators. We know V initial is 8 meters per second, V final is unknown. And potential energy we're not going to include because potential energy at the beginning and potential energy at the end are the same. There's no overall change. And it looks like that's the only type of energy changing. So would you consider this an open system or a closed system? Yeah, I think this should be an open system. And why is that? What's making this open? Yeah, the friction, the air resistance is causing energy to enter or leave. Is this gaining or losing energy due to the air resistance? Yeah, we've got energy leaving the system. So I'm going to draw an arrow going out. And we can label this work done by air resistance. Since work is leaving the system, would you expect kinetic energy to be increasing or decreasing here? Yeah, energy leaving the system means some form of energy has to be decreasing, and kinetic energy is the only one that is even changing. So we should expect the object to be slowing down overall. The final speed is going to be less than 8 meters per second. Any questions on that diagram so far? So let's see if we can turn this into an equation. We know that change in E total should equal work plus heat. Use a different color there. Change in E total should equal work plus heat. The only type of energy changing here is kinetic energy, so that's just delta KE, nothing else to add. There's work, but there's no heat. And how do we write out change in kinetic energy? If what we care about is velocity, how do we relate change in kinetic energy to velocity? Do we have a formula for that?
1/2 mass change in velocity squared.
Yeah. And that's equal to the work done by air resistance. And let's go ahead and fill out that delta V squared. That's V final squared minus V initial squared. And we know the mass, we know the initial speed, and do we know the work done? How much energy is being removed by air resistance here? Yeah, we're losing 20 joules of energy on the way up and also losing 15 joules of energy on the way down. So we can set this equal to 35 joules in total. Although it's energy leaving the system, so how would we write that? Yeah, we'll call that negative 35 joules. So we know the work. The total work done by air resistance is negative 35 joules. Negative because the energy is leaving the system. So we should be able to solve for V final since that's the only unknown left. We know mass, we know V initial, we know work. So before we even plug in any numbers, just working with variables, how would you isolate V final here? How would you undo all those other steps? You could multiply the m over 2 by both of those, but I think it would be easier to get rid of it because we're trying to isolate V final. Our goal here is to isolate V final. So I would look at it in terms of what's being done to V final and then undo all those things. Like if you look at this in terms of order of operations, what's the very first thing being done to the V final here? Yeah, it's being squared. And then what's the very next thing being done? Yeah, V initial squared is being subtracted from it. And then what's the next thing being done to that whole thing? Right, multiplied by m over 2. And since the multiplied by m over 2 is the last thing that was done in terms of arithmetic order of operations, that's the first thing I would undo. You could certainly distribute it to both of these terms, but since we want to isolate V final, I think it'd be easier to just get rid of that m over 2 first by multiplying both sides by what? What's the opposite of multiplying by m over 2? Yeah, dividing by m over 2, which is the same as multiplying by what? If you're dividing by m over 2, that really means you're multiplying by what other fraction? Multiplying by 2 and dividing by, yeah, multiplying by the reciprocal, 2 over m. So let's do that to both sides. Multiplying both sides by 2 over m. On the left side, the times m over 2 and the times 2 over m cancel out. On the right side, so we're left with v final squared minus v initial squared. On the right side, we've got work times 2 divided by m, so 2 work over m. And then what? What else do we need to do to isolate v final? The problem with the square root here is that if we try doing a square root now, you could certainly take the square root now, but that's going to cause problems because there's no easy way to simplify square root of things added together. Square roots don't split up over addition. But yeah, let's get rid of that v initial squared by just adding v initial squared to both sides. Plus v initial squared plus v initial squared. And then that'll give us v final squared equal v initial squared plus 2 work over mass. And at that point, now that we've got v final squared, we've just got something squared isolated on one side. Now I would take the square root of both sides. So square root of the left side equals square root of the right side. So v final is going to equal square root of this whole thing, v initial squared plus 2 work over mass. So that is our formula for our answer. And we can now fill in the numbers to get the actual v final. Any other questions on that so far? So let's fill that in. Square root of v initial squared plus 2 times work, which is negative 35 joules, divided by mass, which was 5 kilograms. So that's square root of 8 squared would be 64 meters squared per second squared. And then 35 divided by 5 would be 7, times 2 is 14, so minus 14. And then joules is kilogram meters squared per second squared. So the kilograms cancel out, you get meters squared per second squared. And then we can subtract those. We get square root of 40. And then meters squared per second squared can be pulled out of the square root as meters per second. So square root of 40 meters per second, which is going to be somewhere between 6 and 7. Any questions on the algebra there? Or any other questions on that problem in general?
On the quiz, it says that the correct answer is 7.1.
Did I subtract that wrong? You got 35 joules, 5 kilograms, 8 meters per second. So 64 minus, is that 14? Because we got 35 over 5. Seems like we should end up with square root of 40. Am I missing something here? Oh, that's right. 64 minus 14 is 50. Thank you. So yeah, square root of 50 meters per second. So yeah, that will be slightly more than 7. Yeah, that should work. Square root of 50. Any other questions on that? All right, then let's take a look at that other quiz question as well. The, where was it? The two spring mass systems. This one? So what are we trying to figure out in this one? If we've got these 3 springs, 3 different springs with the same mass attached to each one, what do we want to figure out here? What's our goal? Yeah, we want to find the maximum displacement, or at least rank the maximum displacement. We're starting with each of these mass on a spring at equilibrium, and we're giving it a shove. We're assigning each one of these an initial speed. So you can imagine these blocks all start off attached to the spring at equilibrium, and we give them an initial speed. Maybe we give them a kick to start them moving. And we want to know, how far does the mass go before it comes to a stop and gets pulled back? So I think it would be useful to think of this in terms of conservation of energy. We can treat the situation as shown here as initial. What would we treat as final based on what we're trying to find? If we take a look at the same situation, we've got this wall, this floor. If based on what we're trying to find, how would you describe the final situation, or the situation you would call final? We're trying to find the maximum displacement, right? We know something about the initial situation. Maximum displacement is what we're trying to find, so I would call that final. If we wait a little while, the mass is going to be moving and stretching out the spring, so the spring gets stretched out. Stretch out beyond the location we're calling 0, because the initial location is at equilibrium, so I would call that x equals 0. But the final situation is stretched out beyond equilibrium. So x final equals, we don't know. The maximum displacement is what we're trying to find. So there's some location where the mass reaches that location. It has stretched out the spring as much as it can. And if it has truly stretched out the spring as much as it can, what's its final speed at that instant? If this is the maximum displacement, if this is the furthest it can possibly go, how fast is it going? Yeah, that's going to be at 0 meters per second. Because if it wasn't going at 0 meters per second, if it had any non-zero speed, that means it's still in the process of moving. And if it's still moving, it hasn't reached its maximum displacement yet. If you're looking for maximum displacement, we want to look at where does it come to a stop. It's been traveling, it slows down, comes to a stop, and it's about to turn around. We're looking for that turnaround point, that furthest it can get from equilibrium. You can also look at this in terms of calculus. If you're trying to maximize a function, if you think back to calculus, just beginning first quarter calculus, if you're trying to maximize a function, if you want to find the maximum value of a function, what do you do to that function? Like if you just got some function, and you want to find its maximum value, what's important about the derivative at that maximum value? What's the slope at that point? Yeah, the slope is 0. If you've reached a maximum or minimum value, the tangent line at that point is flat. Same thing here. At this minimum, the tangent line is flat. So if you're looking for a maximum or minimum value of a function, set the derivative equal to 0, and then solve for the input. Take the derivative of the function, set that derivative equal to 0, and solve for input. But in this case, the function is position. We're talking about position as a function of time, because the position is changing as time passes. So in this case, the derivative would be dx dt, how far it travels divided by how much time it takes. And what do we call that? What do we call distance traveled divided by how much time it takes? If you know how far an object travels and you know how much time it takes to do so, what do you get if you divide those? Distance divided by time. Yeah, that is exactly velocity. Distance divided by time, or more formally, the derivative of position with respect to time is velocity. So when we're talking about position as a function of time, then the derivative, the slope of that graph, is the velocity. The derivative of position, dx dt, is velocity. Dx dt is velocity. So when we say to maximize a function, you set the derivative equal to 0, that means if you want to maximize position, you set velocity equal to 0, because velocity is the derivative of position. When you've reached a maximum position, the slope of your position graph has to be 0. And the slope of the position graph is velocity, because that's rise over run is distance over time. So this also ties into the idea that to find the maximum displacement, you set the velocity equal to 0, because velocity is the derivative of displacement. Any questions on that so far? And that's generally what you want to do anytime you want to find the maximum or minimum value of some variable. Set the rate of change of that variable equal to 0. And then that'll give you an idea of what's going on when that variable reaches its maximum value or minimum value. So let's try that. Let's assume that the final situation is x final equals some unknown maximum displacement. Final speed is 0. And if we treat that as our initial and final situations, we can use conservation of energy. What types of energy are changing here? Yeah, we've got kinetic energy and we've got spring potential energy. Since I think we're assuming this is a closed system, yeah, friction and air resistance are negligible. So we can treat this as a closed system. The mass is, that block is changing its kinetic energy because it's changing how fast it's going. And the spring is changing its spring potential energy. Since it's a closed system, those changes have to add up to 0. And we can fill in formulas for those. Kinetic energy, as usual, half the mass times change in squared speed. Spring potential energy is half the spring constant times change in squared displacement. So that's our equation then. Half the mass times v final squared minus v initial squared plus half the spring constant times x final squared minus x initial squared adds up to 0. Also, everything here has a divided by 2 in it. So to simplify that, I'm going to multiply both sides by 2. So you just get mass times v final squared minus v initial squared plus spring constant times x final squared minus x initial squared equals 0. So there's conservation of energy so far. Any questions on that up to this point? And generally, I would recommend solving everything you can with variables and then plug in the numbers at the very end. In this case, we don't even have any numbers to plug in, except if some of the values are 0. 0 is important. If some of the values are 0, I would go ahead and plug those in. Like, what values do we know are 0 here? Yeah, specifically the final velocity is 0. V final is 0. And also, what else is 0? Yeah, x initial is 0. Since those are both 0, we can just leave them out. So we're left with mass times negative v initial squared, so negative m v initial squared, plus k times x final squared minus 0 equals 0. And we're ultimately trying to solve for x final. So I'm just going to add the mv initial squared term to both sides. So we get k times x final squared equals mass times v initial squared. And then what? What else do we want to do to solve for the final displacement, the final x value? How would you isolate x final here? Yeah, divide both sides by k. And then what? Yeah, take the square root. And the square root here, if you're taking the square root of something that's just multiplication and division, square roots do distribute over multiplication and division. If you've got like square root of a times b, that is the same as square root of a alone times square root of b alone. And likewise, square root of a over b is the same as square root of a alone divided by square root of b alone. You can't distribute square roots over addition and subtraction. That doesn't work. But square roots do distribute nicely over multiplication and division. So if we take the square root of both sides, on the left side, that cancels out the square root. And on the right side, we get square root of each term individually. Square root of m, square root of v initial squared, and square root of k. Also, since we've got square root of v initial squared, we can just cancel out the squared and square root. So it looks like the final displacement is going to be square root of m divided by square root of k times v initial. Any questions on that so far? So let's see if we can apply that to all three of these situations, because we've been looking at this just in terms of situation A, with mass m, initial speed v, and initial or spring constant k. But we're going to be modifying those. The thing is, since we did this in terms of variables, this same result is going to apply to all three of these situations. We're just going to have to modify the values. For instance, in part B, we're taking half the speed and doubling the spring constant. So let's see what happens there. We are decreasing the spring constant, decreasing the speed, and we're increasing the spring constant. We're looking at a slower speed and a stronger spring. If you decrease the initial speed, what would happen to the final position? If you're decreasing the numerator and increasing the denominator. In general, if you've got some fraction, what happens to the result if you decrease the numerator? Yeah, you get a smaller number as a result. So decreasing the initial speed is going to make the final displacement smaller. And I think that makes sense conceptually. If you launch the mass at a slow speed, it's not going to go very far. Versus if you launched it faster, it would go further. So slower initial speed leads to smaller x final, smaller displacement. Also, what happens if you increase the denominator? Increasing the denominator also leads to a smaller number, right? So a larger denominator leads to a smaller result. And I think this also makes sense conceptually. If you increase the spring constant, you're talking about a stronger spring. If you got a stiffer or sturdier spring, it's more difficult to stretch, more difficult to compress. So you're using a stronger spring and you're launching the object more slowly. It's not going to go anywhere near as far. So both of these changes, the slower speed and the increased spring constant, those both act together to make the final displacement much, much smaller. So we should definitely be able to say that the final displacement for B is much smaller than the final displacement for A, because both of these changes are acting together to make the displacement smaller. You launch it at a slower speed and you're using a stronger spring that holds it back more. Any questions on that so far? Then let's take a look at situation C compared to situation A. We're still using the same mass, so square root of m doesn't really matter. We're launching it at a faster speed, so we're increasing the initial speed. And we're also using a stronger spring, specifically 4 times as strong. So we've got an increase in the numerator and an increase in the denominator. If you're increasing the numerator, that's going to make the result larger. If you're increasing the denominator, that makes the result smaller. So this is kind of ambiguous. We're going to need to actually look at exactly how it's changed. We can't just say, oh, they're changing in this direction, so the result is going to be changing in this direction. We've got one effect that's trying to make it go further, launching it faster, and one effect that's trying to make it go less far, using a stronger spring. So we're going to need to compare those changes. The speed is increasing, but it's increasing by how much? How much is the speed increasing if we're comparing C to A? We're changing from what initial speed in A to what different initial speed in C. Looks like we're comparing V to 2V, right? So that's just a multiplier of 2. We got times 2. So the speed is changing. If we're comparing A versus C, the initial speed in C is twice as much as the initial speed in A. So twice as much initial speed, that alone would suggest twice as far of a distance for X final. But what about K? How much is K changing from situation A to situation C? What's the multiplier there? From K to 4K, it looks like we've got an increase of times 4. So K is increasing by a factor of 4. It's getting 4 times as big as it was in situation A. But the important thing going on here in the denominator is that the K is in a square root. So we're increasing K by a factor of 4. We're multiplying it by 4. But the overall denominator is being increased not by times 4, but by times square root of 4. In other words, the denominator is only increasing by a factor of 2. So we're increasing the numerator by a factor of 2, and we're increasing the denominator by a factor of square root of 4, which is also 2. So overall, X final gets doubled and also halved. We've got a times 2 and a divided by 2. Those end up canceling out. So for C, the result is exactly the same as it was for A. Twice as fast of a speed and 4 times as much of a spring sturdiness end up canceling out completely because the spring constant is inside a square root. So it looks like X final for C is going to be exactly the same as X final for A. They will both stretch out the same distance. Any questions on that? All right, then that's it for today. Feel free to email me if you have any other questions, and I will see you next time. You're welcome.